Hello and welcome to this problem-solving video on rotational equilibrium, translational equilibrium, and of course, along with that rotational aspect, torques. So in this example, what we're going to be doing is hanging a sign. And what we would like to know is, okay, there's going to be some rope. It's hanging on to the sign. The sign is then just loosely balanced against the wall, and there's some normal force exerted by the wall. And we want to know how much is that normal force exerted by the wall on the sign. Okay, we're going to want that in terms of the angle theta that this rope is making, and W, the weight of the sign. There's a little hint. We should remember the reason that this whole thing potentially won't fall down is because there's some friction exerted upwards from this wall. In order to address this problem, we need to start thinking about what are the various forces that are acting, in addition to this tension that's clearly drawn in, acting at some angle theta. So we've got essentially a couple told to us in the question. Actually, we've got all of them told to us in the question. So there's a weight W, which acts down. And remember that since we're doing rotational equilibrium, it's not enough to know what the forces are. We need to know where they act. So if we look at this thing, the gravity should always act, or the weight force, should always act at the center of mass of the object. We haven't been told too much about the sign. We'll go ahead and assume that the center of mass of this object is in its center. So then gravity acts straight down. Okay, so that's the weight force and where it acts. And then we need to think about the friction force and the normal force that we're told also exist. So we know there's some friction force between the wall and the sign, which is pulling up, and we know there's some normal force going that way. But in order to think about where we can place them, in order to figure out this normal force, we have to think about what's going on. So if this thing were about to spin, then what would happen? Which way would it spin? Well, the only thing it can do is that actually this thing would rotate down and out this way. The sign would fall out from this side, which means that this upper corner is the last bit that's going to be in contact with the wall. So given that, we'll go ahead and put our normal force and friction force acting at those points. Now, why do we get to do that? So we're essentially thinking about what is the worst case scenario in order for this thing to not spin. And the worst case scenario is that it is just on the verge of tipping. Okay, so initially, when you think about it, you know that really there's like little bits of normal force acting all along there. Okay, between the wall and the sign, roughly drawn in the right places. But then as I get closer and closer to the tipping point, to the point where this sign starts to move away, the wall, or the line of contact, becomes a bit, you're imagining it going to this in the next instant. But it hasn't quite gone there. It's still touching. But as you move, you start reducing the force that's exerted here because, of course, you're sort of lifting that piece off, and that force goes over there. And as you continue this, you can actually get right at this critical point where you're still touching the wall, but there's no force of contact. So this may seem a little strange. Well, how can there be contact but no normal force? Well, think about it this way. If you were out in space, there's no gravity pulling down, so there'd be no real need for the floor to exert a normal force on your shoes. But you can, in fact, be touching the floor, right? And then if you actually push on the floor because you're in space and there's no gravity, you then start flying off and you leave the floor. Because the moment you push on it, it does exert a normal force, which results in acceleration applied to you, and so you accelerate upward and fly away. But the point there is that you can actually have contact. Your shoes can be in contact with the floor. As long as you don't push down on the floor, you'll stay in contact with the floor, but the force between you is actually 0. Okay, well that's true for anything in free fall, really. And in particular, it's true for these bits of the sign, as long as it's being just on the verge of tipping. Okay, so we'll put the normal force acting all at that corner. We'll put the friction force all at that corner as well. And then that will give us our understanding of where the forces go for this problem, from which we can then start thinking about applying the fact that we are not rotating and what's going on. Okay, so we can go ahead and just put those forces on, because, as we said, the sign wants to swing out that way. So those forces go right there. All right, so now we've got all the forces in place. We need to pick a pivot point. And the whole point here is the sign is not rotating. So if it's not rotating, then it's not rotating about any point. We can choose any pivot point we like. Now in this problem, the actual pivot point is a good choice. So we identified that corner as being special because that would be the last one in touch. So we'll sort of pick that as an important point, and we'll go ahead and use that as our pivot point. Because from that pivot point then, we can start thinking about the torques. And how did we choose this one? Well, think about the equation for torques for a second. It's R, F, sine of theta, so the angle between them, or R cross F, if you like cross products. So if we make our choice for the pivot point be such that forces act at the pivot point, so that R is 0, then those forces won't contribute to torque, and it makes our life easier. So by choosing our pivot point right there, then we can eliminate 2 forces right away. Okay, so then we need to look at this thing and figure out what are the torques. We have to be careful of the signs in this problem. So let's think about which way each force is trying to make this thing rotate. So with respect to our chosen pivot point, if the weight force is pulling down, well, that will make us rotate in this direction. And the tension force, on the other hand, is pushing. There's a component going straight towards the wall, which is not rotating us. But there's also a component upwards, and it's actually acting over here. So that's making us turn this way. Okay, so we can put in those arrows. Weight force makes us turn that way, and the tension makes us turn that way. So we can write down what the torques are in this case. Okay, so remember that an anti-clockwise torque is taken positive, and a clockwise torque is taken to be negative. So the weight force is a negative torque, the tension is a positive torque. Okay, and what RF sine theta really says is, give me, say, the distance times the perpendicular component of the force. Okay, well, that's pretty straightforward. For the tension, the perpendicular component of the force is actually sine theta times t. The radius at which it acts is L. So now we're doing the sum of the torques, which is L t sine theta. Okay, and then the weight force acting in with a negative torque at a distance of L on 2, and the magnitude of the force is W. So here, what I've done is actually reinterpreted this to say, give me the force times the perpendicular distance to it. So I've imagined this weight force is acting straight down. So the perpendicular distance to it is just this line here, this part of the distance. Because I could draw my radius vector to be this, and I can decompose that into a component like that and a component like that. And so this part is the perpendicular distance, but that's exactly halfway between, so it's L on 2, and the force is just W. Okay, So this is how we can play around with this equation to not really have to worry too much about signs and things. Okay, we couldn't get away from it here because we had to project part of the tension. Okay. So the sum of the torques is this, and if it's not rotating, it had better equal 0. Okay. Now, that's kind of great, except that for this pivot point, we've taken out all the forces that we wanted. So how are we going to turn this into something about the normal force? Well, there's a little bit of a trick here. Okay, this is a perfectly valid approach, but it requires one extra step in order to find out what the normal force from the wall is. But let's continue on with this. So let's figure out, say, what the tension is. The tension in the string is, because that's sort of the only really unknown thing. Like the mass of the sign would give us the weight, so that's supposedly given to us. So let's go ahead and figure out tension. So because all this stuff equals 0, I can set this equal to this, and I can divide through by the L sine theta, so I get W2 divided by sine theta. Okay, and so then I can turn that into W2 well, it's W2 divided by sine theta, which is cosecant theta. Okay, or just simply W on 2 sine theta. Okay, so that's great. That's the magnitude of the tension. So what can we do? How are we going to turn that into something about the normal force? And here's where translational equilibrium comes into play. So this was rotational equilibrium. Translational equilibrium is the same statement, but for the sum of the forces. And of course, this is actually a vectorial equation. So it really means that 0 is equal to the sum of the forces horizontally and similarly vertically. But horizontal is all I care about, because the normal force exactly opposes the horizontal component of this tension force. So this tension force has a horizontal component. The normal force is equal to and opposite that. Well, the vertical component of the tension force was T sine theta, the horizontal component of the tension force, and it's acting to the left. So there's a negative T cosine theta. And the other bit that is acting to the right, so we'll call that positive, is exactly this thing that we want, F of the wall on the sine. So again, it's equal to 0. I can move it to the other side. So I know that F wall on the sine is just T cosine theta. But previously, I turned that into W2 on 2 sine theta. So I can just write that W on 2 sine theta cosine theta. And I can turn that, if I want to, into cotangent. So it's W on 2 cotangent theta. Right? So we chose a pivot point, we worked with it. It was great because it got rid of some forces, but unfortunately it got rid of the forces we are actually interested in. So we used some translational equilibrium to bring that force back in and get an answer. All right, so let's go ahead and check this claim about the pivot point by choosing, let's say, the upper right-hand corner. If we choose that upper right-hand corner to be our pivot point, then we've got a force of gravity, the weight force, acting down at a distance over here. So it's going to actually make us rotate in this direction, which is anti-clockwise. So that's going to provide us with a positive torque. The tension is acting at the pivot, so R is equal to 0, so it's not producing any torque. FWS is acting on a line directed towards the pivot, so that's also not going to produce any torque. The explanation there, the easiest one to give, is again this idea that you're treating a rotating door like a sliding door, And of course, if you do that with a rotating door, it's not going to rotate. You need to actually pull or push on the door in order to make it move. You can't just kind of try to shove it into its hinges. So we know that FWS is not doing anything because another way of thinking about it is the angle between them is actually 180, the sine of which is 0. So even mathematically it works out. Okay, so that's two forces gone, and then we just think about FWS FR. Well, that is actually trying to make us rotate like that. So just like that. So that's going to be a negative torque because that's clockwise. So we're going to go ahead and use these and write down our sum of the torques. So we know that the sum of the torques have to be 0 if we're not rotating. So we know, what do we have? Well, we've got, the weight force, not mg. I mean, it is mg, but we don't know m. We just want to leave that as w. The weight force times the distance at which it acts. Well, that's this perpendicular distance again. It's L on 2. And then we have to subtract off this clockwise torque from FWS of friction acting at a distance L. And that's supposed to equal 0. So then we can quickly conclude that FWS FR is equal to just W on 2. Okay, which would be great if we knew what the coefficient of friction was, because then we could figure out what the normal force is, and that's exactly the force we're looking for. That's what this FWS represents here. That's the normal force from the wall on the sign, and that's what we're looking for. But we don't know mu, and we're not allowed to leave our answer in terms of mu, so we've got to keep going. So here again, we need to apply some translational equilibrium. So let's go ahead and do that. The sum of the forces horizontally, say. Well, that gives us what it gave us in the previous case. It tells us that FWS is equal to the tension cosine of theta. Okay. Sum of the forces being 0 in the vertical direction. Well, that's the friction force going up. Plus there's another force going up, which is the tension, the component of tension rather, T sine theta. And that has to equal the overall force down, which is W. Okay, so great, now we're getting somewhere. From this one, we know what FWS friction is. It's just W on 2. So we have W on 2 plus T sine theta equals W. We can subtract the W on 2 and find out that T is W on 2 sine theta, which looks familiar. We can then put that back into our horizontal equation. So FWS is supposed to be T sine theta. So now we know that T is W on 2 on sine theta as before. So we end up with W on 2 cosine on sine for theta. And we plug this in for this T here. So it's just this W on 2 cotangent theta again. Okay, and therefore we've verified our claim. Doesn't matter what the pivot point is, you can get the same answer. The choice of pivot point does determine how much effort it takes. So if you choose it wisely, you get away with less effort. If you do it a bit difficult, if you do a different pivot point, it might be a bit more difficult rather. But the choice just sets how difficult it is. Now there's one other thing that we can do with this question, which is actually we can figure out now the coefficient of friction. So we said over here, if we knew the coefficient of friction, we would have the normal force. But now we've got the normal force. So FWS of friction is FWS times mu. So mu is just FWS friction divided by FWS. So that's W2 divided by W2 cotangent of theta. So W on 2 divided by W on 2 cotangent theta. which is equal to tangent of theta, because the W12's cancel. Okay, so we now know the coefficient of friction as well, which is nice. Supposing that was actually part of the question, then this way we've now got all the information. From the other approach, we would have had to still consider the vertical direction and do that extra bit of work anyway in order to get to mu. So if we were asked about what is the coefficient of friction in terms of all of these things, then actually it wouldn't matter which pivot point we chose, because we'd have had to go through all these equations to get to there. Otherwise, we're sort of happy. So hopefully that's helpful.